Now let's look at the bottom-up approach to solve this. What we do in this approach, we divide this into subproblems. We find the longest decreasing subsequence for subarrays like 0 to 1, 0 to 2, 0 to 3 and so on. And we store the result in 1D array. So if we have these results, we check at any position, can we increase the value of LDS by adding current element to the sequence. For instance, if we are at position 3 and we already have LDS for subarrays 0 to 1, 0 to 2, then we will check can we increase the LDS by including this element in the LDS. If we can, we will add 1 to the LDS, which is larger among the values that we have already stored in LDS array, and get the LDS for the subarray 0 to 3. So the logic is pretty much same. Let's see how we actually implement this. So what we do, we will take an array that will store the LDS values for all the subarrays. Like at index 0, we store LDS for array 0 to 0, at 1 for subarray 0 to 1, and at 2 for subarray 0 to 2, and so on. So we will store them instead of calculating it again and again. So what we do, we initialize the LDS array with 1 and then we will try to maximize it. We will start comparing the values. We take I and j pointers. J gonna point the position for which we will calculate LDS and I for going through every element present before j. So let's start. For subarray 0 to 0, the longest decreasing subsequence will obviously be 1. So we start looking for position 1, so j is 1. We check if 8 is less than 20. Yes, so we can increase the value of LDS by including 8. So we add the LDS for element 0 to LDS for element 1. So it becomes 2. That's the LDS value for subarray 0 to 1. Now we increment j and we check if we can increase the LDS for subarray 0 to 2. If we compare 12 with 20, it is less than 20, so we can include it. So we add the LDS for 20 to this one, which is 1 again. So we update 1 plus 1 to at index 2. Now we increment I. Why? Because we need to check if we can increase the LDS even more. Now we check if 12 is less than 8. Nope, it's not. So we cannot include the 12 with the LDS sequence for subarray 0 to 1. So we don't update it. So the LDS for subarray 0 to 2 is 2. So increment j again and start comparing it with every element present before it. So 16 is less than 20. Yes. So we add 1. So it becomes 2. Then we check if 16 is less than 8. Nope. So do nothing. If 16 is less than 12. Nope. Again do nothing. So that's the LDS value for subarray 0 to 3. Let's move forward. Increment j. We check if 10 is less than 20. Yes. So we add 1 to LDS for 20 and increment I. If 10 is less than 8, nope. So we do nothing and increment I. If 10 is less than 12, yes. So what we do, we add 1 to LDS for subarray 0 to 2, which is 2. So it becomes 3, which is greater than current one, which is 2. And our goal is to maximize LDS, so we pick 3 and update it. Then we again increment I. Again we check if 10 is less than 16. Yes, so we add 1 to LDS for subarray 0 to 3, it will be 3. We compare if it is greater than current one, which is not, so we do nothing. So by this point, we have LDS for subarrays 0 to 1, 0 to 2, 0 to 3, 0 to 4. So we keep on moving, we increment j and we compare 9 with all these previous elements and we maximize the LDS for subarray 0 to 5 and we get 4 here. And we continue, we increment j and we maximize the LDS for 18 and we get 2 here. Again we increment j and we now compare 7 with all these elements and we try to maximize the LDS length for the element 7. So at the end we get 5 here because we can include 7 in the decreasing subsequence. So at the end we can see the max value among these is 5, so the final result would be 5. That is the bottom-up approach.